Okay, so in the previous classes, we had the second order system of x over y was omega n square in s square plus 2. Can you see the screen? That's right. Yes. And I applied here is y, here was y. Okay. F, F, F. So f of s was impulse and the f of s was unit step impulse. And we saw that after implementing these, we got this response for the impulse, and we got this response for the unit step for the underdamped system. What's happening here? For underdamped system. Okay. So when the zeta is smaller than 1. And in both cases, we saw that, as you see from the graph, E steady state error signal is 0 because the output follows the input after settling time. And we defined some important parameters. Tp was pi over omega d, time of the peak, and the overshoot maximum peak in percentage was E minus, we derived mathematically together, 1 minus zeta square in percentage. You have in your notes. And the settling time of 5% criteria we got as 4 over zeta omega n, and for 2% criteria was 3 over zeta omega n. Do you remember that in the previous class? And also we got the rise time, the first time that you have TR. I think that it was, if I'm not wrong, let's look at your notes, it's minus tangent inverse of 1 minus zeta squared over zeta. That's right, it was like this. So now let us continue for our third input to the systems when the f of s is ramp. When it's ramp, f of t. F of t is ramp, so f of s gonna be, as you know, 1 over s squared, as we did for the first order system. So having that, so x gonna be 1 over s squared omega n squared. Again here s minus p1, because we are still in the domain of the underdamped systems. S minus p2. Right? Still we are for the underdamped system, second order systems. So you know that p1 and 2 is gonna be minus, you have a pair of complex conjugate poles located at the left hand side of what? Complex plane. So now we have to decompose this as a over s squared plus b over s, because we have 2 poles in the origin, plus c over s minus p1 plus d over s minus p2. And these are complex poles, as you see here. Can you hear me, guys? Yeah, S minus P1. These are parentheses, that's right. Oh, yeah. So I just decompose as in the previous class. Look at the notes. When I was applying this step, remember? Yeah, yeah, sure. Yeah, I know. So you're gonna have, it's gonna be S squared S minus P1 S minus P2. You're gonna have here A in S minus P1 in S minus P2 plus BS in S minus P1 S minus P2 plus CS S minus P2 plus DS S minus P1. Here we go. Okay. And this is S squares, not S, because they have no S. CS squares minus DS squares is minus 2. Okay. CS squared, DS squared. So obviously this numerator equals to omega n squared numerator. So can I go to the next page? Yes, everybody. Okay. I assume that you agree. So I'm writing here for simplicity A S minus P1 S minus P2 plus B S S minus P1 S minus P2 plus C S squared S minus P2 plus D S squared S minus P1 is omega n squared. So now you can sort it based on S cube plus S squared plus S plus constant number. So S cube C S cube plus D plus B. Here we go. This right now S squared A and minus B P1 plus P2. If you do the operation here, you're gonna get that. Okay, minus C P2 here. Okay, and minus D P1 from here. Now S gonna be from here. S gonna be A minus A P1 plus P2. I'm gonna double check later, okay? Here just I'm writing A from here. S. Here you're gonna have plus B P1 P2 from here. And nothing. And finally, the only thing that you have as a constant number is A P1 P2 equals to omega n squared. Let me double check everything. C plus D plus B S squared gonna be A minus BP, BP2 in SS square minus CP2 minus DP1 square. S gonna be minus AP1 plus P2 plus P1 P2 BS. That's it. Okay. Now from previous class, you know that P1 in P2 is omega n square. If you remember your notes, I calculated that. So from here you get that the A is equal to 1, as we expected. So what we have here is this. D plus B plus C is 0. B P1 plus P2 plus CP2 plus DP1 is minus 1. I'm just putting the other side, A, right? Or it is 1, not minus 1. This is 0, it's gonna 1. And you get B P1 plus P2 is P1 plus P2. Sorry guys, this is B P1 P2 is P1 plus P2. So this is, you know that this is omega n square. And the P1 plus P2 means zeta omega n plus I omega d and minus zeta omega n minus I omega d. Gonna be minus 2 zeta omega n. Right? So this is minus 2 zeta omega n. So you get from here that your B gonna be minus 2 zeta over omega n. Bingo. So now I'm taking this out. So what you're gonna have C plus D is 2 zeta over omega n. I'm moving B to the other side. And CP2 plus DP1 gonna be I can leave it like this because for simplicity, because I'm simplifying everything. We know the B, but I'm putting here, for God's sake, P1 P2 CP2 plus DP1. So it's gonna be minus B P1 plus P2. I'm just putting B from here. Minus, gonna be like this. I'm moving B to the other side. So B is minus P1 plus. And this one gonna be this. So now you can find from C and D from here. See what I'm saying? Let me do this. And let me delete this for simplicity. Minus P1 plus P2 over P1 P2. You see? So how to do that? I'm just multiplying the both sides of this by minus P2 and then sum. If you do that, you're gonna have D P1 minus P2 equals to minus plus P1 plus P2 divided by P1. This with this goes. Minus and plus. Minus B in P1. B was what? What was what? B was P1 plus P2 divided by P1 P2 multiplied by P1 plus P2. It was B, right? So from here you can find D. Some things based on P1 and P2. And if you implement here, you can find C. I don't care about the final answer. Okay, you can simplify the whole working. So, being said, these are constant numbers, right? P1 and P2. I mean that we have it. Okay. So, being said, now we have the answer. X equals to A was 1 over S squared. B was minus 2 zeta over omega n over S. I'm just replacing here, guys. Where is it? Here. C, a constant number that you can calculate. C over S minus P1. D, a constant number that you can calculate based on P1 and P2. Here we go. Now, let's go to the time domain by Laplace inverse. You see that the x of t gonna be this term, as you know, it's gonna be ramp. This term gonna be unit step 2 zeta omega n in step or 1. This term gonna be c e p1t plus d e p2t. We did it for that. Because these are complex conjugate, this gonna gives you guys at the end gonna give you eventually this e minus zeta omega nt plus sine omega dt plus phi, because these are complex conjugate, as we did for the unit step. Means it's gonna, this decaying term when time goes to infinity, this goes to where? This goes to where? 0. This term goes to 0 when time goes to infinity. Okay, guys. What was the name of this in the control engineering? And what was the name of this? Look at your notes. Look at all of you here. What's the name of this x transfer function? Input. What is closed transfer function? Look at your notes. Input or output? Output over input. So this is the output of the system, that's right. So this is output. What's the name of this? Yes, input. F. Ramp. Input. And again, when I'm plotting this, omega n square in s square plus 2 zeta omega ns input output. So input minus output gonna be how much? Error signal. So t minus x of t when t goes to infinity, I'm saying, gonna be how much? 2 zeta over omega n. Why I'm saying t goes to infinity? Because I say this goes to 0 at infinity. So on the other hand, what is this? What is this here? Based on the block diagram, look at here. F is equal to t. T minus x is how much? Is how much? Steady state error signal. Gonna be 2 zeta over omega. You see that despite the case of the unity step and the impulse, we have a steady state error signal, which is a function of the damping ratio and natural frequency of the system. Any second order system, as I'm going to teach you RLC circuit, as I'm going to teach you the tank of the fluid in series, they have the natural frequency and the damping ratio. So if I want to plot that, I'm going to go to MATLAB today. Okay, so you see that if I want to plot x over t, this is input to the system. So it says you have some transient oscillation, decaying oscillation, sine omega t, but gonna vanish for transient. This is transient, as you know, transient response. But after that, see, look at here, you have some oscillation, and then you're gonna have steady state error signal, constant, like this, right? So this is constant, constant, constant. And it's obvious because it says x equals to t minus lower than that. This is your x. This is your x. This is your y is equal to t, lower than that mathematically. So what is interesting, guys, is that for the first order system, when x over y was 1 over tau s plus 1, steady state error signal was tau. But what's the main difference between this and second order system? I'm going to show it here also in MATLAB. In the first order system, we had no oscillation in transient response. It was like this. But here you see oscillation because of this sine term, because your system is underdamped. We will go to the critical damp overdamp eventually, but that you see that the oscillation goes away. For the underdamped system that we are talking, so you have this oscillatory behavior as transient and then vanishing because of this decaying term. Understand, everybody? Yes? Clear? So let's just go to the MATLAB. So first is obviously when you go to MATLAB, MATLAB because it has no ramp input in the coding, we're gonna use our tricks. That's right. Omega n square in s square plus 2 zeta omega n s plus omega n square. So because this is ramp gonna be 1 over s square, we're gonna write as 1 over s in 1 over s. So this is unity step. So you have x over unity step, because we have the code in MATLAB, gonna be omega n square in s square plus 2 zeta omega n s plus omega n square. So you have third order systems, right? So your num c gonna be 0 0 0 omega n square. Your then gonna be 1 2 zeta omega n square, and there is no constant number here. and 0. Third order system. See what I'm saying? Yes. So let us visualize what we did, and I'm gonna change the damping ratio because to see the effect of that on the transient response. Let me thumbs up. Okay, so what we're gonna do for the coding, I'm gonna say CLC clear all, close all. So, and I'm gonna say zeta 1, I'm gonna say 0.05, means what I'm showing is we have almost very low amount of damping, and the zeta 2, I'm going to increase that to 0.3. Okay, zeta 2. Then I'm going to say omega n is I don't know, 10, obviously in radian per second. I have to use my comments. And having that, we have num equals to 0, 0, 0 omega n squared. That's right, third order system. And then 1 gonna be 1, 2 zeta 1 in omega n, and in omega n squared, and 0. And then 2, because I want to compare this. And then 2 gonna be zeta 2. That's it. Okay, everybody? So then figure 1, first let time, because I have to plot ramp. Time equals to 0.01 and to 15 seconds, and the y input to the system is time, ramp. That's right, ramp. So it's gonna be figure 1. I'm gonna say step, num, and then, and time, hold on, obviously then 1 with the low amount of damping, and step, num, and then 2, and time, and hold on, plot time and in red grid. There we go. Okay, so I'm gonna save it as ramp under damp second order system. Okay, so if I run this, what was that? Oh, there's a typo here, and this is too much. I have to make it 4. Okay, let's magnify. So guys, if you see that if I zoom this in, okay, here we go. This is the red line is what is this unit step. This is for the zeta 1, the blue line. When the zeta is 0.05, you have low amount of damping, so you see more oscillation. This orange line gonna be brown line. You see that I increase the damping, so you have a low level of oscillation. You see after this point, after 2.5 seconds, this settles down, and you have constant. You see constant error signal for the yellow line. It's both are under damped system, but this oscillation vanishes here. But the oscillation of that, the low damping continues until when? Until still we have it here. Look at here. Still we have it transient. So let me run it for 15 seconds, see if this settles down. Yeah. See, if I zoom this in for the low damping, so see, it takes a while, 10 seconds that this settles down, that there's no oscillation anymore. And you have constant time constant, you have a constant steady state error signal. So you see that there's a difference between the step input of the second order system, which is under them, and the first order system. In the first order system, let me plot it here. I want to visualize. I'm gonna say num of first order system was 0, 0, 1 after transferring to the step. That's right. And say its tau was 2 seconds. Okay, time constant. And it's gonna be tau, and it's gonna be 1 and 0. If you got your notes, you see that. And I'm gonna make it 3 because I already have it. This is for first order system. Now I'm gonna plot against each other. 3. I'm gonna comparing the first and second order system with underdamp, obviously. This was the time constant, remember? For the time constant of first order system. Okay, so if I do this, here we go. You see that if I zoom this in, this is the first order system. There is no oscillation, remember? But for the underdamped system, there is oscillation to be settled down eventually, but has the steady state error signal. Remember? So the error signal of the first order system was, remember, I'm writing here, E of the first order system was tau. Tau is 2. But the error signal of second order system was 2 zeta divided by omega n. See what I'm saying? So let me calculate it here. See what? Steady state. Say 2 zeta 1 over omega n. So let me run it and see the answer. So a steady state signal was 2. His was 0.0067. Let us see it. Exactly. Here is 10. Here is 8, 2 for first order system. But this is going to be very small amount of numbers, steady state signal. See? Here we go. It has a steady state signal, but very low value, exactly 0.0067. See, constant. But see what I'm saying? So when you come to control class, you're gonna, oh, why did I close it? You're gonna learn how to design controller to make the both goes to this, to the input to the system, the both of them. For more visualizing, let me put this as then 2 with more damping. Okay. Here it goes much better. See the oscillation here, and then goes there. And you see that when increase damping, your error signal also increases. See, 0.4. There, everybody. So, because I'm sharing with you, let me put a legend, and I'm going to change everything to second order system. Legend is zeta 1 is 0.005 and 0.3 and this is the input to the system. Y is equal to T. There we go. Again, there's typo. Here we go. See, zeta 1, we have to fix the zeta 2 and y is equal to T, but you have to magnify it. To magnify it, because I'm going to share with you, let me change this to again to 4 seconds, and this is zeta 2. Okay. Here we go. Zeta 1, zeta 2, and y is equal to T. Okay. So now let's go to our Simulink. You see, I'm opening the ramp of first order system. So, and I'm gonna save this as, come on, yeah, save as, why I'm doing that, because I wanna, okay, ME430, I'm gonna be second order system. Okay, so I'm gonna keep it as the first order system here. Okay, and here I'm gonna change it. I'm gonna change this to, we have to use the open loop transfer function. That's right, not the closed loop. That's why here is the second order system. Gonna be 1, 2 zeta. Zeta I'm gonna put as 0.1 and omega n I'm gonna put as 10 again, and 10 square means omega n square. See here, guys. Oh, sorry, and 0. See here, we are using the open loop transfer function. Omega n square s square plus 2 zeta omega n s. There's no constant. So, and omega n square, I'm gonna be 10 score. So because omega is 10, I'm going to damping ratio of the 0.1, and here we go. Now and then. Okay. So now if I plot this for 4 seconds, okay, that's the difference between them. Remember, again, we are putting the open loop transfer function. Here we go, as you expected. Red line input, blue line the underdamped second order system, and settles down here. Settles down, let me tell you, here almost, okay, at 3.5 seconds. And this is the first order system, that there's no oscillation. So the main difference between the first order system and underdamped second order system is there's no oscillation for transient response. Let me run it for 10 seconds, that settles down. There we go. See? Oscillation here, no oscillation, settles down, settles down. Okay? Understand everybody? Yes? One of the things that, I save you, okay. One of the things that I want to teach you in the MATLAB when you are doing the modeling of the system, sometimes guys, if I increase this to, where's time? To 20 seconds, you see that you cannot read the data until you zoom in. Okay. See, everything is very narrow. So one of the things that you can do is you let me show another example. I'm gonna say time equals to 40 and y equals to time sine of time, okay, and I'm gonna put this exponential of -2 in time. Okay, we have two ways of plotting this. One of them is that I say figure 1, plot time and the y. Okay, great. Example, plotting. Example of plot. Okay. And this is 0.001 to things. And when this is vector, you have to put this for the multiplication. But this is vector. Okay, we are vector by vector. Learn this, okay? So if I want to plot this, it's gonna be like this. Okay, but this is narrow. See what I'm saying? So you can say semi-log x or y. Guys, now look at how it looks like. Do you see, everyone? I plotted in the log scale, and you can see what's happening really here. Semi-log x. See what I'm saying? Because here we know that it's 0. I don't care. I want to see what's happened here in the transient response. See what I'm saying? Yes, everybody? Can you hear me? Guys?
Yeah.
Oh, okay. See, also we have semi-log y, but it's gonna be funny here. This is the command that I want to see. It's gonna be funny. So what always we do, and we do this for the graduate school when we go to plot the power spectrum of a signal. Power spectrum or the Fourier transform that we're gonna do that. So Similark is a good command that you can see what's happening in the graph that is very narrow and you cannot see the information inside. So I wanted that to teach you in the modeling of physical systems. Okay? Clear? So that's it. I'm done. Next class, we're gonna go over the second order system. Cool. I'm gonna share the files with you. Any questions you may have? Yeah, so actually we did several times, but I'm just doing it here. Okay? So for the closed transfer function, you have to know the closed transfer function. But for the closed transfer function of second order system, this is closed transfer function, second order system. And we are putting the ramp itself. We don't need to change it, that's right. Because in Simulink we have ramp. S square plus 2 zeta omega and S. I think we did. We did for the step? Or we didn't? We did, I think that's right. 1 plus G. We can calculate G from here, that's right. Open loop transfer function. If you do that, your G, as you have in your notes previously, is like this. Omega n square in S square plus 2 zeta omega ns. So it's num when I put in Simulink, gonna be 0, 0 omega n square. It's then gonna be 1, 2 zeta omega n and 0. Because it is a constant number. Yes. You got it? So again, I'm emphasizing for the open loop for the Simulink, you have to put the open loop transfer function for unity feedback. For coding in MATLAB, you have to put the closed loop transfer function for the command up step. Simulink has a step, has ramp, but has no impulse and the parabolic. And I taught you in the class how to generate them in the Simulink and MATLAB. If you were not in the class, please go to the previous topics. I exactly said how to produce those. Okay? We do have the step and ramp, but we don't have impulse. And actually, we have impulse, but for the discrete time dynamics, not for continuous. But the parabolic, we don't have it. We have to generate those by changing the transfer function. I'm going to do for the parabolic the next class, and you're going to see how I'm going to do that again. Okay? Because we don't have parabolic. See what I'm saying? Okay. Thank you. Thank you, guys. See you. Bye.